Hey guys, so we'll probably just wait about 1 or 2 more minutes for people to come in. All right, guys, I think we'll kick it off there. Welcome all to this afternoon on Thursday, the 18th of June, to talk about indoor 3D modeling with the Flyability Elios 2. Let's get right into it. So today you're speaking with myself, Harrison. I'm account manager for both Flyability and the majority of Sphere Drones' enterprise clients here at Sphere Drones. And we're thankfully joined by Gregory, who is a professional services engineer at Flyability. So Gregory mainly leads client demonstrations around the world. He's built out a lot of the technical documentation for the Elios 2, and he is one of the leads for photogrammetry at Flyability. So thankfully, he was able to join us it's an early morning over in Lausanne, Switzerland. So happy to have him here, and yeah, we'll get right into it. So, bit of an agenda for today. We're going to be talking about how photogrammetry is being used to build indoor 3D models for industrial applications. We're going to give you, Gregory's going to run you through some 3D modeling process data. We're going to talk a little bit about why the Elios 2 and how it's been purpose built for confined space inspections, how Sphere Drones are able to provide local support and services, and then we're going to jump right into Q&A for the most part. So just a quick touch on Sphere Drones and how we support our clients here in Australia. So we offer sales, repair and maintenance, training services, consulting, rentals, on-site support, and enterprise agreements. So Sphere Drones, we currently have 2 offices set up at the moment in Sydney and Perth, with aspirations to be opening up in a few more in the next year or 2. So look, I'm going to hand it over to Gregory and let's get straight into the meat of it all today, so we can see some of the indoor 3D modeling.
All right. Hello, everybody. All right. There we go. I hope you can all see my screen. It should show up right now. So, well, today we'll be talking about the indoor modeling capabilities of Elios 2, and I'll start off with a couple of well, answers, hopefully, to the question of why would you want to do that, and then I'll get into some use cases where I show examples of how to actually do that and what the results are. So answering the first question, why would you use it? Well, it really depends on what industry you're in, what your expectations are. Basically, for us, the answer was as simple as because we can. So we've had some issues, well, some questions come up from customers back in the Elios 1 days, where we had the camera was basically behind the cage and partially obstructed by it. So unfortunately, that precludes any kind of useful photogrammetry work with it. But with Elios 2, the camera is actually partially outside of the cage, and that gives you an unobstructed view, which can then yield some more interesting footage that can be used in photogrammetry. And one example that springs to mind is just a couple of months before we released Elios 2, we had a question from well, quite a large company that manages several power plants. The way these chimneys are usually decommissioned is they put a small roof on them and then they just leave them out on the plant property, because dismantling them would pose too much risk to the other buildings on the site. So one of those chimneys had been sitting around for a couple of decades, and they were curious to see what it was like on the inside. Of course, they couldn't use rope access workers because it had been in such a dilapidated state. We could only send in Elios 1, which did the job, but well, the video quality wasn't great. The lighting isn't awesome. With Elios 2, what we would be able to have been to do was exactly what they asked us actually during the tender, was to make a 3D model of the inside of the chimney, as they had done on the outside with just standard outdoor drones. And we would have been able to present them a whole orthogonal view of the inside of the brickwork, which would have been a lot more interesting than just a bunch of 10-minute videos of the drone bouncing around on the inside. So for us, that was really the number one advantage, is you can organize your data. Instead of having a bunch of 10-minute videos, you have a 3D model. And the way these photogrammetry software usually work is you can navigate a 3D model, click on any point on that model, and that gives you a blow up of all the pictures that are taken near this point and actually contain the points you clicked on. So you can look at the point from different angles without having to skip through a video, or actually several videos to find that point again. An example also is of this. I think this is a gas-fired power plant. You can see the burners on the left-hand side here, and the pipes containing the water on the right-hand side. The thing about these burners is there's about 100 of them in every boiler, and they look absolutely identical. So looking at a video of inspecting these boilers one by one, inspecting these burners one by one, can get pretty disorienting after a while. And if you can tie those all together in one model, it makes navigating the inspection a lot easier. And this is the roof structure of a silo. Obviously, that also has the same issue. All the beams look exactly the same. If you can create a 3D model of that, you can actually do the inspection and then use the 3D model to identify the location of any defects. Another advantage is, of course, you can make measurements. So by default, since you don't have GPS data indoors to scale your model, you'd have to use a reference dimension. But when you've got a reference dimension, you can scale the whole model to that, and you can sort of extrapolate or interpolate other dimensions that you find in that model. And on the right-hand side here, you see an example of an elevator shaft, where we've probably taken the total height of the model as a reference, and then you can actually locate the position of various defects, or maybe also brackets that have been installed for the previous elevators. You can actually locate those quite precisely inside the model. Another example is something we've discussed in a little bit more detail in a previous webinar here at Flyability. This is the top of a chimney. So you can see the refractory material, and this is the sky as you're looking up out of the chimney. And the green area is actually hand drawn in the photogrammetry software. In this case, it's Pix4D, over the area that has missing refractory. So if you scale that model, in this case, we use the height of the chimney to scale the model. You can calculate exactly how many square meters of refractory are missing. And this is the same, well, not the same chimney, but it's also in a refinery. This is an FCC unit riser for people who are in the industry. If you're not, it's a steel tube covered in this hexagonal mesh and refractory, and it contains high pressure, high temperature oil products and a catalyst. So there's actually quite a high flow of material going through this, and it causes this erosion of the refractory material, which is there to protect the steel pressure vessel basically from the heat. So this is quite important that the refractory stays intact. And what we discovered are these this kind of erosion, this pitting in between two layers of the stuff. And the question was, looking at the video, is this a problem, right? You need to know how deep the erosion is to figure out if it's going to make it to the next maintenance interval, to the next shutdown. And look, just flipping through the video frame by frame, it's pretty difficult to get a view of what exactly you're looking at. But just with this 3D model, it becomes obvious pretty instantly that it didn't go all the way through, and it was probably fine for another 2 years, which was the next scheduled maintenance. Then there's this indoor stockpile. Measuring outdoor stockpiles is pretty straightforward with drones. However, indoor stockpiles require indoor drones, and that's where Elios 2 comes in. So it's the same principle, different drone. And most photogrammetry software has a built-in volume measurement where you can just click around a heap of raw material, and it'll sort of tell you what the volume of that is. Another advantage is that you can use the 3D models to actually map the entire shape of the structure. So this particularly is interesting in mining, where well, on the right-hand side here, you see the drone inside a mine. It's pretty abstract because of, well, the darkness, obviously, but this is the next slide should show an animation. I don't know the frame rate with which this is getting through on your side, but it shows the virtual camera flying through a model of a stope, which is in underground mining. There's an extraction technique where you basically blast a huge cavity in underground just to extract the material. So this is sort of explosively removed bit by bit, and it leaves behind a giant cavity. For obvious reasons, this cavity is off limits for any kind of human inspection, because first of all, you've got perhaps unexploded explosives hanging around. You've got the risk of falling material, and it's not a secured environment where you would want to hang around with ropes. So the drone is an obvious choice, and making a model of this will allow you to first of all figure out whether the material has been removed in the right places, if there's been any dilution in your ore. For example, you can see there's a slight bend in that top tunnel there. Maybe they left behind some of the valuable materials as well. So getting a good view of what's going on in those is typically useful. Another advantage is you have a color image. Like, this looks pretty black and white because it's rock, so it's gray. But you have a color image of the minerals that you're basically looking at in that stope. So geologists can perhaps deduce whether they're actually following the right track with the exploitation of this material. Another use case where you would want to use the actual 3D model is, for example, when you're planning maintenance or design changes. I'll give the example of a turbine hall of a thermal power plant. Those tend to be built between 30, 40, 50 years ago, maybe. And if you're lucky, you've got as-built plans. Otherwise, you've only got the architectural plans of how they intended to build them. In the past 30 years, maybe not all changes have been documented. Maybe someone installed a ceiling fan somewhere that doesn't show up on the plans, or maybe AC units, that sort of stuff. And for example, if you want to upgrade one of the turbines or even maintain them, usually these turbine halls contain significant surface area that can be used, can be converted into a work area for these kind of overhauls. You'd want to know if you can go ahead and dismantle the equipment in the space you've got available. So making a 3D model will really help in figuring that out. And then there's the sort of the bit of a geeky use case where you want to track changes. There's a huge archiving potential. Like every plant has got their folder structures full of pictures from maintenances and overhauls of 30 years ago, where you see basically the same infrastructure being inspected with people with from that era, and they're seeing the same kind of damage. And these pictures are extremely useful because it allows you to track changes of, for example, a crack that is not critical yet. You can actually follow that throughout the ages on that documentation. Making a 3D model of that crack, obviously that's going to give you more information, and I think where that really comes in handy is if the day comes that we are using machine learning and AI algorithms to determine whether a crack is critical or not. If you have an existing library of learning material for those AI algorithms in the form of 3D models, that's going to give you a lot more information to process and to train your algorithms with. So that's a bit of a future-proofing nerdy topic, but definitely something worth looking into. So I think we can get started with the examples of some of the inspections that we've done over the past couple of months since we got started with photogrammetry. These examples have been dealt with in previous webinars. Actually, if you go on the Flyability website, you can see the Photogrammetry in Action webinar, which is available online for free. We did a sewer where basically it was about data localization. For example, you spot the missing brickwork. You want to know how many meters from the entrance of the sewer we found this we spotted this missing brickwork. There's a more detailed use case, more detailed story about the FCC unit where we did this refractory coating analysis, and there's also a more detailed story of this refractory coating in the chimney where we did the surface measurement. So this is the entire chimney where before we just saw the little the tip where you had the refractory missing. This was I think was a 60 or 100 meter chimney. For today, I prepared a bunch of new use cases for you. So we'll be doing a silo where it's all about volume measurement. This is a 14-meter diameter bulk material silo. There is an ore pass in a mine where we did surface mapping of a hangar in the ore pass. And we'll be looking at a cave. Basically, this is a nearby cave here in Switzerland that we often use to test our new firmware or test our new drones. And we did basically the experiment of trying to map the whole thing. So just as a demonstration is how you would go about doing this with a stope, for example. Right, moving on to the silo. Well, you can see on the right-hand side, it's one of those giant concrete cylinders you often see. In this case, it was in a cement factory. so it contained limestone. And the whole point was to measure the volume of these, which is not straightforward, because the material either has, like when you're filling them up, they form this pyramid of material, and as you're emptying them out, it sort of forms a pit in the middle. So it's quite difficult to estimate them just by sticking a stick down them and saying, okay, we've got 2 meters. So you want it to be more accurate, you have to actually measure the surface of the material. So that's what we went ahead and did. We sent in a drone, and that's what they look like. Basically, on the inside, you can see this heap on one side and this pit on the other side, and quite dusty on the inside, but didn't seem to affect the end result too much. This is the model that came out. You can see that it had some trouble modeling the walls, but that's fine. We're not interested in those anyways. We're just interested in the surfaces of the material. So if we clean that up a bit, this is what we end up with. And you can see the green points here are the path of the drone as you were flying through that environment. Just wiggling it about a bit. So this is a GIF animation that's going to go on forever. Just to show you like the 3D effects of the path. So it spent some time trying to map the walls, sort of just to make sure I've got the roof in there as well, or the ceiling, because that's what you actually want to measure up to, because you want to measure the material that's missing, not make any assumptions of what's underneath, right? So then once you've got the walls mapped, you basically you snake down into the bottom, and you're basically done. So this was one, I don't know, 8-minute flight or something to map this thing. So this is what the interface looks like. You can click around and then basically extrude this surface down onto the surface, and then the surface of the material, and that's going to give you the volume of this negative space in the top of the silo, basically. So this indicates that in order to completely fill this one, you would have to add 810 cubic meters. And the reason we sort of do it top down is these usually taper down into a cone at the bottom. So instead of having to make assumptions of what exactly kind of how far the cylinder goes and then how much volume is in the cone, well, you can just say if it's full, it's going to have X 1,000 cubic meters, and in order to fill it, just subtract those 800 from the total volume, and that gives you your current stockpile. On this particular inspection, we also had a GeoSlam LiDAR, which is, well, a LiDAR is a radar with lasers. If you're familiar with the technology, it's a handheld unit. You can wave it around and it basically scans the entire environment. They're pretty heavy, so they don't fit on the Elios 2. You can't put them on there, but we lowered it down with a rope, just as a zero reference measurement, because these are quite accurate. And you can see it also scanned some of the top structure of the silo where we would have been standing, piloting the drone. And on the right-hand side, there is a heat map that shows you the accuracy of the photogrammetry point cloud compared to the LiDAR point cloud. You can see most of the surface is sort of in the 25 millimeter accuracy range. Most of the inaccurate areas are the walls of the silo, which are quite noisy because they were usually quite far away from the drone when we were filming them, and sort of this back side of the heap, on the reverse slope, didn't get to properly film that, so it's quite noisy as well. And my theory is that because it's so noisy, there's a lot of peaks. There's where the point cloud usually it wants to be a surface, but in this case, well, it sort of noised out into a point cloud, and that's what's introducing a lot of this inaccuracy. Just a recap of the project stats. This was one 8-minute mapping flight. We exported 650 images from the video. And the scale reference, well, actually, I can show you that. It's in this image. That's the sort of weight, a bob weight that we introduced into the tank, and it has two white stickers. One of them is here. The other one, I think you barely can see it. I'd say like 1.5 meters apart, and you can just click on those in a model and say, okay, well, this is going to be both your z-axis and this is going to be 1.5 meters. So that scales the whole project and allows you to actually export well, useful values from the volumes. I processed this on my very modest laptop, which is an i5 processor, 8 GB of RAM. It took about 7 hours. Next project is the ore pass. So if you're familiar with mining, you'll know what an ore pass is, and you'll know why it's bad if you have a hang up in your ore pass. But I'll just briefly explain it. This is a schematic of a mine. Basically, and I was surprised to learn this when I first heard about it, that in order to get the material out, first they dump it all the way down through this giant chute throughout all the levels. It goes into a crusher, it goes into an elevator, and then it goes up through the elevator shaft. This means that all the ore that's being extracted from a given mine has to be dumped through this this chute. And if you only have one of them, and if it gets clogged up, then well, that's bad because you won't be able to extract any material until you unclog it. So this was sort of exactly what happened here. And the way these hang-ups are cleared is you drill an intersecting tunnel or a borehole, stuff that with explosives, and hope that sort of flushes it out. Either that or drill a second ore pass, which can take you know, a long time, and you're not making any money while it's hung up. So there's definitely a rush to fix this as soon as possible. Anyways, in this case, we wanted to first of all identify the location. Say it's so X meters up from the previous level, and as a bonus, we also identified and mapped the shape of the hang-up material and sort of the shape of the surface of the hang-up. So this is the video as I'm flying up through this tunnel. You can see actually several interesting features, parameters on this cockpit view. You can see the camera angle here. So I'm looking up at 81 degrees. So I'm flying mostly upwards, which means the material is sort of hanging in space. It's really weird how it sort of forms this what's called a cohesive arch of small material. On the bottom left-hand side, you can see the altitude of the drone with respect to where it took off, like on the previous level, which was the haulage level. And then on the top, you have like flight time, battery, etc. And putting all the images of this one flight into Photogrammetry allows you to make this model, which is well, it's impressive. You can see exactly what shape the ore pass has. If there's any like dog ears being formed, you can also pick them out, you know, see them on that. I was flying a little bit too fast to make a really good model. If I had the chance to go back there, I would probably do this in 2 or 3 flights, so that there's less motion blur, and that just gives you generally a better model. But for this purpose, you know, you're just interested in figuring out what this distance is. And actually, if I'm perfectly honest, you don't need photogrammetry for that, because you've got this onboard altimeter here that tells you exactly, well, within a few percent what that altitude is. What did prove to be quite useful for the geologists was the model of the tip of this model. So that's the actual position of the hang-up, and you can see sort of the shape and features of this hang-up. So because this is quite a small model, it's like 200 images. It took me about 2 hours or something to process on my laptop. So I had it ready on the very same day of the inspection. So this caused a lot of oohs and ahs among the geologists during the briefing of the inspection. Just a few project stats. So this was one 9-minute flight. It was about a kilometer underground, so extremely hot, 43 degrees C, and near 100% humidity. So the drone would have kept flying all day, but I wouldn't have in those conditions. It was quite uncomfortable. There's about 300 images that were exported for the top of the. I'm talking about the top of the hang up here, the small model you saw. 300 images exported, and it takes about 2 hours. It took about 2 hours on my laptop. We use the ORPAS diameter for scale because on this model, well, there's no real other given dimensions. And since this is a board one, the diameter is quite consistent. So this is really like the cool feature is that if you keep projects small and simple, you can actually like speed is quite important here. So that the fact that it was being evaluated on the same day of the inspection is quite important as well. Okay, so the last one we'll talk about is a cave. It's not, well, it's something we did just as an experiment, basically. It didn't have any practical use other than to give us a bunch of experience on how to make models of larger areas. So this was sort of pretended it was a stope, and we wanted to do 100% model of this entire cave area. So it's about, I guess, about 80 meters long by 20 meters wide by 30 meters high. So it's comparable in size. And this is the flight path we eventually ended up taking. You can see it's a pretty organized, grid-shaped, more or less, flight path. Then there's some freestyling as I fly up that shaft. It's sort of a spiral pattern, and then there was a way to pause this. These two, vertical tunnels that go into the rock there. You basically just fly in and back out again. So there's not much room to maneuver in those anyways. So you can just go in and out. But yeah, you can see it's a pretty complete model. This is an animation of the inside, and it looks very well lit because you're basically filming the rock that's in front of you. You're stitching a bunch of well lit pictures together because you've got the onboard lighting. But as you're flying, it's completely dark. You've just got like the surrounding rock around the drone that's illuminated, and everything else is pitch black. So it's really weird seeing it perfectly illuminated like this. As a scale reference, we again use this bob weight, so that gives you a scale. It also gives you a z-axis, which you also need to manually insert. There's two black stripes there, which are poorly visible. Also, what we learned from this is you're better off putting these retroreflective material stickers on those instead of making black stripes, because you can see those from much further away. So actually, one of the conclusions from this is that I always carry a fishing line with a bunch of these reflective material stickers on every meter, so I can just hang it up wherever I need it. Really going back to the last thing, we set out to do 100% inspection. You can see there are some holes, and I did my best to hide them in this animation, but you can see right there where there's this platform, there's a big hole there, and there's a bit of a crack coming up just there, right? That's basically just a coverage issue. So because I didn't fly my drone enough there, and for obvious reasons, it would have blown wet leaves onto the other pilots. We were about 4 people flying simultaneously at that day, just to test new firmware. So that's why we didn't map that. And the missing part in the crack is basically just poor flight planning. I should have made a few passes there instead of just one. just a quick overview of the project stats. These are 7 mapping flights, 2,600 images, and it took about 16 hours on my laptop. So this is the sort of stuff that you just run overnight. That's pretty much it for the cases. I just want to finish off by saying, if you want to get a training on building 3D models, you can contact us via our website. We have a website, well, we have a page dedicated to the indoor photogrammetry training, and just to keep up with the times, we've also made this available as a online remote webinar training. So if you're interested, let us or contact Sphere Drones, and they will forward you to us. So I guess Harrison, that's it, and back to you.
Great, thank you, Gregory. What we're going to do now, before we move on to the next section and then to Q&A, is I'm just going to run a couple of poll questions to get a gauge for who we have here today. So the first question is, do you hold a remote pilot license? I'm just going to run that quickly. Great. So the second poll question is, which industry do you most commonly operate in? Okay. The third poll question is your site using drones already? Okay. Okay, so give me 1 second. Okay, so why do we use the Elios 2, not only for photogrammetry, but for indoor inspections, indoor inspections? So Flyability as a company purpose-built their drones for confined space in indoor inspections, and purely and only that. They're a strong team of, I believe, up to about 85 employees now, with 60 to 70% of those being engineers, who all work day in, day out to build a drone that is purpose-built for confined space inspections. So we have the GPS-free stabilization. We have the distance lock. Now, from a photogrammetry perspective, the distance lock allows for frame continuity, which will improve the quality. We have the camera and the lighting. So the 4K camera on the drone means that you're getting a really good capture, a really high quality image. The oblique lighting isn't something that you can really compare to any other drone on the market if you were to use it for indoor inspections. The photogrammetry mode, which has been recently released by Flyability, is purpose-built for photogrammetry, and what that does is it slows down the yaw of the drone so that you're getting a nice, clean, and consistent capture. So how does Sphere Drones provide support and services to Flyability? So we are one of the official repair and maintenance centres in Australia, with our headquarters in Sydney, but also our office in Perth. We have 2 of our technicians that have been over in Lausanne in Switzerland for training to be able to repair and provide maintenance on both the Elios 1 and the Elios 2. We're also a certified training centre, so we've also had pilots go over to Lausanne to be able to provide all levels of training for Flyability products. General support, so we've got a very strong team of technicians, engineers, pilots who can all provide a very high level of support for not only the Flyability products, but all the other drones that we know and love, such as DJI. Spare parts, so having the offices both in Sydney and Perth, we stock a majority of spare parts, and we've got a large stock. I believe we've got a lot more coming over in the next 2 weeks, so that we're able to provide batteries, spare motors, propellers, cages. So the latter two are what generates a lot of interest. So we are able to provide short-term critical rental services for clients that are looking to onboard the Elios 2. And we are also able to provide client demonstrations. So we provided, I believe, we've probably operated about 25 to 30 client demonstrations on clients' assets of all different kinds. Okay, so plenty of experience between both of our offices and our pilots to be able to support the Flyability products. So we've got about 15 minutes left, and what I'm going to do is I'm going to run through one more poll question, and then we're going to go straight into Q&A. So the question is, would you like a Sphere team member to contact you to schedule a demonstration on your site, not only of the photogrammetry aspect, but also if you're interested in an Elios 2 visual inspection demonstration? So run that for about 10 more seconds. So we'll jump, there's plenty of questions that have come through, so we'll jump straight into them. So Gregory, there's a question that's been asked from a Reef, I hope that I'm pronouncing that correctly, is how many pictures can be captured in one flight time battery?
It really depends. So if you export every single frame, then you can, in a 10-minute flight, you'd have 600 seconds times 30 images. So I think the number of pictures is pretty much unlimited because you're exporting them from the video. And the surface area that you're covering in one flight depends on the quality of your model you want. So I guess it's difficult to really stick a number to that. But it's
Sure.
it is sort of different using Elios 2 rather than other drones where you would plan your flight on software and then just push a button and it executes the little grid pattern as you would have it for outdoor stuff. So you have to keep pointing. I mean, you'd have to really work the sticks to keep pointing the camera and the drone at the things you want to capture. Make sure you have enough overlap during the flight, and then later on you would you can actually play around with the overlap by tweaking the export frame rate of the video. So it's a different work process. So I guess the limiting factor is the number of pictures which can be processed in your photogrammetry software.
Awesome. Thanks, Gregory. I guess would it it might be great if you can just give us a very quick overview of I guess general practice of what frames you would be taking out when going into your Pix4D, for example.
Yeah. Usually I export with a frame rate of between 1 frame per second to 5 frames per second, something in that area. So if I'm just flying down a tunnel straight, you'd want you want more frames than when you're doing sort of flying at right angles to a surface.
Sure. So Gregory, there's another question from Gaurav, which is when we're looking at that ore pass case study that we were looking at, was that utilizing range extenders?
Yes, the ore pass was using a range extender. So we put a range extender between the ore pass, like underneath the ore pass, because I wouldn't want to be standing underneath there while flying the drone. So we sort of stuck one in there. Usually that's done with a long boom. So you'd tape the range extender to a long boom and then just shove that into the underneath the ore pass like you would, shove a pizza into an oven. So you could maintain your safe distance, and if stuff comes crashing down, you wouldn't be directly in the path of all the debris. Sure. And the range extender, it has basically it has a 20-meter cable, so it allows you the antennas to be, rather than on your control unit, it allows them to be 20 meters down the cable. So that's if you're standing around the corner, then that's enough to maintain safe distance.
Sure. So there's another question here. Another question just about the captures that we looked at today. Were any of those using any external light sources apart from the onboard lighting on the Elios 2?
The silo that you saw, that had one, I think it had like a 100-watt LED light, like one of those construction lights in one of the manholes in the top. All the other ones were just using the Elios 2 onboard light.
Sure. And would that be a recommendation if you had the ability to provide more lighting? Is that something that you and your team would recommend?
Yeah, well, it makes your life easier basically, because it extends the visual range of the drone, if that makes sense, because you're not looking at the reflections of your own light, but you're looking at sort of a uniform. If you can add external lighting, it just makes the process a bit more robust.
Sure.
But it's not strictly necessary. So you saw in the cave, it worked fine without any lighting.
So there's a few questions around for the photogrammetry, whether you're utilizing the photos or the video. Just to clarify, you are pulling frames from the video.
Yeah, so at least in Pix4D, we have basically the camera model in the database, because you need a camera calibration model to map the sort of intrinsic distortion of the lens and the camera And we have that for 4K video, full HD video, and also the 12 megapixel stills that you can take during the flight. But basically the gain in resolution from 4K to 12 megapixel isn't, in my opinion, isn't really great enough to merit like not using the flexibility of exporting frames later on, which is,
Sure.
I mean, first of all, you'll be spending a lot of time pushing the picture button because there's no way to automate that. And then if you mess up the overlap, well, then you can't really adjust that by exporting more frames because the pictures you've taken are the frames you've got. So.
Sure. It might be great as well. There's a question around different softwares. Gregory, do you want to just talk for a moment to the relationship with Pix4D and if any other softwares have been used to produce photogrammetry models with the Elios 2?
Yeah, so well, Pix4D basically is, it works with non-geotagged images, and it has our camera calibration file. Those are the two advantages. There are some other software, for example, I think Bentley context capture also works without georeferenced images, and there are some others out there as well. I think I don't have any experience with any of them except for the freeware stuff, which I used a few years back. That's called Free SFM or Open SFM or something like that. But yeah, we basically use Pix4D in-house, and we have basically we sort of collaborate because they're from the same city, same country, so it's pretty easy to communicate with them.
Using the case studies for examples, are you able to comment on the type of accuracies that we've been able to achieve to date with the photogrammetry for the Elios 2?
Yeah, that's sort of,
or in general terms, doesn't have to be using the case studies.
Yeah, well, in the theoretical, mathematical accuracy is 3 times the ground sampling distance, which is the size of a pixel, as it appears on if you take a, so it's sort of difficult to put like a millimeter value on that, because in theory you could have a 1 millimeter accuracy, but the effort required to achieve this would be, I think, impractical in the real world. So we've done some laboratory tests, where we've put some scales on a palette, and I think there's a LinkedIn video that we shared a few months ago about that. But that's for small scales. If you want to, like the accuracy we've achieved in the field would be sort of between 10 centimeters, around that level. So for a relatively large model, because that's also the thing, as you get bigger, the accuracy sort of becomes lower and lower, because you tend to fly further away from something, so your GSD goes down. You tend to have less references on large models. So I think 10 centimeters on a like 50-meter scale model would be accurate. And then if you want to really, like the FCC ring that I showed you, like the thing with the hexagonal meshes and refractory, that was a 60 centimeter diameter tube. So you could get your camera right onto the concrete. And I think it's accurate to say that's a 1 millimeter accuracy model, because it's so tiny. I mean, you're gonna have very short distances between the camera and the thing you're filming. So that gives you a high GSD, so that gives you a high accuracy as well.
Sure. Another question that's come through is, how do you deal with the homogeneous environments when creating the 3D models? So if you're operating in an area where maybe there's some shiny metals, what's the results like there?
Well, shiny metals just they don't work because the software can't really get any reliable fixes on the points that it's seeing. So it's kind of like when you've been doing outdoor photogrammetry, you'll know that some things like forests, especially when there's a lot of wind and they're always moving, that doesn't work, and water doesn't work. So that just ends up as a hole in your model. And reflective surfaces like shiny metal or glass, that it's the same thing. So that's one of the limitations, actually. Yeah.
Okay, we'll probably run maybe one or two more questions. So there's a question is from Graham to improve the quality of the 3D modeling. Would you do 3 or 4 flights and then upload all of the videos to Pix4D?
Yeah, so if you have a large model that requires these like several flights to have complete coverage, I'm guessing that's the question.
Yeah.
So there's several ways of doing it. What I always try is to export all the images, rename them, and then put them in one folder and see what Pix4D makes of it. And sometimes you're lucky and it just stitches the 3 flights together. There are some tricks you can use to increase your chances of this. If you always take off from the same spot and sort of follow the same path during the first like couple of meters of your flight, you'll get a higher chance of the flights automatically matching up. And if that doesn't work, you'd have to stitch the models together using manual tie points, which is a little bit more labor intensive, but it once you get the hang of it, it doesn't take very long time.
Sure. So just seeing if we have one more question. So just a more general question that's been asked around the temperature range of the Elios 2. So the temperature range is recommended 0 to 50 degrees.
Yes. So the drone itself can fly in 50 degrees. The issue is the batteries. Obviously, if they start off at 50 degrees during the flight, they're going to get to 80, and that's a bit toasty. So what we do in cold weather or hot weather is we have this one of those insulated boxes with either warm water, like it's like a bottle of boiling water if it's cold, or a pack of ice if it's hot, just to keep the batteries at their ideal temperature at the beginning of the flight, and then during a 10-minute flight, they're not. I mean, the ambient is not gonna. If they start out at 20, they're gonna end up at 50 degrees, even without cooling. So that's within limits. But
Fantastic.
Yeah, there's some things to take into account in extreme temperature conditions. It's not straightforward.
Sure. Okay. Thank you. Look, any questions that haven't been answered, I will endeavour with my team and with Gregory to answer them offline. Thank you all very much for attending this afternoon. It's a bit of a later one than usual, so thanks for joining, and stay tuned for one of our next webinars to come out. Thank you.